Welcome to this explainer. I am absolutely thrilled to have you here today. Look, we are constantly hearing these massive, sweeping headlines about artificial intelligence, just draining our power grids and guzzling up our natural resources. But we have to ask ourselves, how much of that is reality and how much is just hype? Today, we're setting the stage to uncover the real, data-backed truth behind AI's actual energy consumption. We're going to look at hard numbers from the International Energy Agency, Our World in Data, and some really cutting-edge research out of Penn State University to give you the absolute clearest picture possible of what AI truly costs the planet. Which brings us right to the burning question, right out of the gate. Does using AI actually harm the planet? Like when you sit down and ask a chatbot to write a recipe or summarize a long document, are you personally contributing to a global energy crisis? It's a hugely complex question, and getting to the answer means we really have to look past the sensationalism and look directly at the data. Okay, let's dive into this, because the actual data here might honestly shock you. When we look at projected global electricity usage for the year 2025, artificial intelligence data centers only consume about 0.5% of the world's electricity. That's it, literally half of 1%. Non-AI data centers, the ones powering your everyday streaming services, your emails, your online banking, they make up another 1%. Meanwhile, the entire rest of the world's activities account for a massive 98.5% of electricity consumption. So, despite the massive surge in AI adoption we've all seen, on a global scale, it is still a remarkably small slice of the overall energy pie. Now, you might be wondering why you see totally different numbers reported in the news. Well, it's really important to understand why the leading estimates diverge so much. The International Energy Agency, or IEA, estimates total data center usage at 485 terawatt-hours, which, by the way, is roughly equivalent to the entire annual electricity generation of Germany. But here's the catch: they exclude cryptocurrency mining. On the flip side, S&P Global estimates a much higher 790 terawatt-hours. Why the massive gap? Because S&P includes the immense energy draw of crypto mining, which uses between 150 and 200 terawatt-hours all on its own, and they use a different capacity-based methodology. When we evaluate AI's footprint, it is absolutely vital to know exactly what is and isn't being counted. Section 2. The cost of one query. Let's transition our narrative away from those massive global terawatt-hours and zoom right down to the personal, everyday level. What actually happens when you, the user, type a single prompt into an AI model? The energy cost of a standard text query on an AI model, think Google's Gemini or OpenAI's ChatGPT, is incredibly small. We're talking just 0.24 to 0.34 watt-hours. To put that into perspective, that is a tiny fraction of a single watt-hour. Researchers at Epoch AI and independent statements from tech leaders consistently land right around this microscopic footprint for a typical simple text request. To make that data a bit more visceral, that 0.3 watt-hour footprint means that your simple text prompt uses roughly the exact same amount of energy as running your kitchen microwave for a single second. 1 second. Or, alternatively, leaving your television on for just 10 seconds. So, if you've been feeling this heavy environmental guilt every time you ask a language model to draft an email, you can definitely breathe a little easier knowing the individual cost is extraordinarily light. Now, what's really interesting about this slide is how energy demand spikes dramatically when we ask AI to perform complex reasoning. You see, not all queries are created equal. A standard query is a fraction of a watt-hour, sure. But if you feed the AI a massive document, say a 7,500-word report, that jumps up to 2.5 watt-hours. And if you ask an agentic AI model to actively reason through a really complex, multi-step problem, the energy draw can surge to 50 watt-hours per request. Basically, the more we ask the AI to think, the harder the physical hardware has to work. But let's contextualize even that higher number, right? 17,000 watt-hours. That is the average daily electricity use per person in the European Union. In the United States, actually, it's about double that. So even if you're sitting there running highly complex, reasoning-heavy AI queries at 50 watt-hours a pop, your personal AI usage is still just a microscopic fraction of your overall daily energy footprint. Section 3. Local grids under pressure. If individual queries are tiny and global percentages are small, we really need to shift our focus to geography to see the real issue. And this brilliantly illustrates exactly where all those billions of tiny queries are being processed. Look at the stark disparity in this data. Globally, data centers use 1.5% of electricity, but in the United States, that average jumps to 5%. Zoom in even closer. In Ireland, data centers consume more than 20% of the entire country's electricity. And in the U.S. state of Virginia, which is a massive hub for tech infrastructure, data centers account for over 25% of local electricity demand. The burden of AI isn't spread evenly across the globe at all. It's highly localized, putting immense, concentrated strain on a handful of very specific regional power grids. And this localized strain, it could very soon become a global reality. Mahmoud Kandemir, a distinguished professor of computer science and engineering at Penn State, points out a really dangerous trajectory here. If the current unchecked scaling of AI hardware and massive model training continues as is, data centers could account for an astounding 20% of global electricity use by 2030 to 2035. That kind of explosive growth would literally require a complete overhaul of our global power infrastructures. Section 4. Hidden costs. Water and waste. It's time to broaden the scope of this explainer, because electricity is only one part of the equation. Up to this point, we've only talked about the electricity used to run queries. But before you can even ask an AI a question, that tiny 0.3 watt-hour query we talked about earlier, it must first be trained. AI model training is arguably one of the most resource-intensive computing tasks on the modern planet. It involves adjusting billions of parameters across thousands of highly specialized graphics processing units, or GPUs. These machines run continuously at maximum capacity for weeks or even months on end. It's an incredibly expensive, energy-dense process that, honestly, only a few massive tech giants can afford to do on a large scale right now. And all that immense processing power brings real physical fallout, which we can basically consider collateral damage. First off, these servers get unbelievably hot. To stop them from literally melting down, advanced cooling systems consume millions of gallons of water, creating severe, immediate risks for regions that are already facing water scarcity. Second, these GPUs are run so incredibly hard that they have really short lifespans, generating a mounting crisis of electronic waste. And finally, replacing all that burnt-out hardware requires mining more rare earth minerals, a process that severely degrades natural environments. Section 5. Paths to Sustainable AI. Let's pivot our narrative away from the environmental problems and look towards some empowering solutions. So, we've outlined the heavy challenges, but it's definitely not all doom and gloom. Let's look at the tangible solutions researchers are developing right now to build a roadmap for the future. Professor Kandemir outlines 3 totally proactive steps. Step 1. Instead of training massive general-purpose models that try to know literally everything, we can develop smaller, highly efficient, domain-specific models tailored for specific fields like healthcare or chemistry. Step 2. We can revolutionize the hardware itself, shifting away from standard GPUs toward brain-inspired neuromorphic chips and highly efficient optical processors. Step 3. We can be way smarter about when and where we compute. By automatically shifting massive AI workloads across time zones, we can align them perfectly with periods of peak renewable energy, basically running the servers when the sun is shining and the wind is blowing. So the absolutely crucial point here is that fixing this isn't just a computer science problem, it's a human collaboration problem. Achieving a true green AI future requires intense interdisciplinary teamwork between environmental scientists, hardware engineers, and policymakers. Funding from agencies like the National Science Foundation and the Department of Energy, paired with university research, is absolutely essential for this. We need incredibly accurate carbon footprint assessments to finally turn these green theories into strict industry-wide standards. Which brings us to our final critical thought for today. The impact of your AI usage isn't just about how much energy is used, but how that energy is made. An AI query powered by a coal plant is vastly different from one powered by a solar farm, right? So the ultimate question we have to answer as a society isn't whether we should stop using AI, but rather, can our rapid adoption of artificial intelligence outpace our ability to green the local grids that actually power it? It is a fascinating challenge, and for sure, one that will define the next decade of our technological evolution. Thank you so much for joining me on this explainer today. Keep asking great questions, and I'll catch you next time.